Hello, everyone. Apologize for the delay. I'm Abhishek. I manage a machine learning team with Twitter. This is going to be the agenda of the talk today. I'll quickly talk about the team to set some context on what we are doing and why we are doing. Then quickly introduce the concept of embedding. I'm pretty sure most of the folks here are pretty familiar, so I'll keep that short. Then I'll go into why we started to work on embeddings and what does it provide to various different teams and applications within the company. Then talk about a little bit of the pipelines that we have built and how that helps us. And lastly, talk about the next steps that we are doing and other things that we are pursuing. So quickly to get going about the team, I'm part of Cortex. Cortex, for those of you who might not be familiar, is the centralized machine learning organization within the company. We have the platform teams as well as applied research within that. As part of this, our team, MLX, our charter and the vision is to unify and advance recommendation systems for all the different products, surfaces within the company. What does that mean and why we think embeddings is a great enabler and tool to able to do that? That's exactly what I'm here to talk about today. First of all, just a quick recommendation system. Why does it matter for Twitter? Where do you see that on the app on a day-to-day basis? Everywhere, pretty much. Home, Explore. On the home, you see your tweets. These are personalized for you. You go to the Explore tab, look at the hashtags, who to follow modules. You have it personalized to your interests and tastes. You get these notifications, emails, on the notifications tabs. Everything is sort of curated to the user's taste. And that's where recommendations come in. You can even think of all the product surfaces as sort of recommendation system in a nutshell. Twitter is a recommendation system in a nutshell. Quickly pivoting to what's an embedding. Simply said, you can think of it as a discrete a representation of a discrete entity in a continuous space. Most often, you would use some sort of modeling to get there. With discrete entities, I'm talking about anything from users to hashtags, tweets, @ mentions, words, if you go one level down. And when you get that in a continuous space, what it really means is that for each particular ID in that discrete space, you now have a representation in a continuous space. What that gives you now is you have the ability to have some sense of similarity or relationship between any two given IDs in that entity space. That is pretty powerful, and we'll get into how we can then actually use that. But this is pretty much what an embedding is. So now, why we really want to actually use them, how are they helpful? I can categorize them in fairly sort of 4 different broad categories. So the simplest being that you can use them as model features in any of your sort of machine learning models, because they have captured, in a sense, some sort of relevant signal from the entities that you modeled against. Now you can use them as input to any of your ranking models, and that has some powerful abstractions to it. I'll talk about that in a bit. Feature compression, this is somewhat of a more Twitter-specific use case because of the scale that we operate our recommendation stack at. And I'll talk about that as well. The main promise there is that if you are able to use this as a feature compression engine, then you can really get some benefits in cost and improve efficiencies. Third, nearest neighbor search. When you actually are able to create these embeddings for yourself and use nearest neighbor search on top of that, that really opens the space up for lots of different use cases. And this has been sort of our focus area for a while now in the team. Transfer learning is sort of, once you do that, you have kind of opened the doors for reuse, because these embeddings that you learn are actually available and kind of applicable across spaces. So they have the promise that you are able to reduce training time and boosting performance across surfaces. I'll give you some examples as we dive into these. Firstly, model features. If you think of any categorical feature, practitioners typically use one-hot encoding to represent those, right? And so what that does is that it's incapable of encoding relationships. These one-hot encoding features are actually orthogonal to each other. One ID compared to another one doesn't really tell you anything in this space. So you're not giving much to your model, rather leaning on your model to do the whole job for you. You're not doing a lot at the pre-processing or the feature generation stage. On top of that, sparsity issues make it less useful for large dimensions. Now, if you're using one-hot encoding, and imagine you want to use your user ID as a feature in there, and for a Twitter use case, let's say there are like 500 million users in my model that I want to use, you're pretty much out of choices at that point. So you can't use the user ID as a feature now. So it enables that as well. And embeddings are output of ML models. So that's why what we do get out of this is we conserve some relationships among entities. That's exactly what was not available to us via one-hot encoding. And you're compressing the sparse input space into a dense vector. And so you solve the second problem there of sparsity and scale. Now, if you're able to compress your 500 million users into 500 dimensions, now we are talking. We can actually use that as a feature in your models. Just to illustrate this with a quick example, let's say we have like 4 users that we are on Twitter that they tweet about, and we want to model them in one of our ranking models, let's say. For the sake of simplicity, let's just say these are only the 4 users. If you were to represent them as categorical features, then all you're left with is a 4-dimensional vector, and you're using that. But let's say now I decompose it into, I'm able to factor this into a 2-dimensional vector, and that embedding can give me some relationships that King James is closer to Steph Curry than Bruno Mars or Kendrick Lamar. As long as I have that and I'm feeding that to the model has a much easier time to get something out of it. So that's basically the promise when using it as features into your models. Now you can get that embedding, put it as a general dense feature in any of your models where you see there is relevance of that embedding that you learned, and you're much likely to do a better job there. Feature compression, just to kind of set up why it's needed and why it's particularly specific to the Twitter scale. You can think of it of any inference stack in Twitter relevant systems as having 2 different set of features. One is sort of the raw offline features. The particular criteria about them is that these are not changing every so often. These are changing only every so often. Let's say 24 hours every month. You're only refreshing this data set every so often. An example could be age of a user, right? You only need to change that data set every once. Let's say at the very best once in a day, 24-hour period. Online features, on the other hand, are something that you need to get into the model at inference time and have the exact value that is there at that moment. A quick example would be number of likes on a tweet. You really want the real-time value there and then, because that impacts the relevance there, right? So once that's there, and for both of these, you have some sort of key value store sitting out there that you're querying at inference time. So what happens really is that if you're trying to increase the complexity of your model by adding more features to it, at Twitter scale, you have a limit, you have a bottleneck there. Because after a certain point, you start incurring cost on your storage cost and your network cost. That means that you cannot go beyond a certain point, because we have tight SLAs that we have to finish this inference in. So what we can do instead is, instead of having the whole space of raw offline features being stored, you can actually embed them from a subnetwork offline. You're basically using the simple thesis that intermediate layers of a deep neural network are actually representations of your input features. The only constraint being that you need to ensure that the efficiency of the model, you're not compromising on that at the end. As long as you have that, you get this ability. Now, what you can do is basically offline, at the same frequency as your raw offline features get updated, embed them, and put that in the key value store instead of the whole raw set of features. And that gives you a lot, because now you can start increasing the complexity of your model by adding more features maybe. And even if you're not doing that, you're saving a lot in terms of cost, infrastructure cost, and if you're reducing your latencies, that also has like compounding effects on your relevance in the product. One note here is that this introduces a lot of complexity, so do it only when you are able to get, you can justify the ROI for this. So this is what it would look like finally. You still do what you were doing for your online features, because you can't really do a forward pass in real time and store that. You get nothing out of that. So you get what you get the promise out of the batch embedding store. OK, the next one, nearest neighbor search. Okay, I'm not talking about these ones. The biggest use case there is it enables candidate generation at scale when used with embeddings. I'll go into candidate generation, but this has been sort of our major focus area for the last 3 to 4 quarters. And I'll go into the details now. In any relevance tag, if I were to visualize sort of the various different stages, and if you have the cardinality of your item corpus at the scale Twitter has it in millions, then you need to have sort of a first stage wherein you're going from millions to about hundreds. And then you can have your ML pipelines kick in, do the heavy ranking, and do all the nice things. A major limitation at the first candidate generation stage has been that how do you scale your machine learning system to be able to do this in let's say 50 milliseconds. Traditionally, what people actually end up doing is that you have some business rules or product, through your product knowledge, you create some heuristics, and you work with them. And that is the place where you're able to go from, let's say, millions to thousands, and then your ML pipelines can take over. And we all know the limitations of heuristics, hard to improve upon, hard to maintain, et cetera. And it's a hit or miss. You do 3 months of work, either it will work, it won't work. There's no path to maybe a V2 of your heuristic, usually. So that's all the problems that there is. Now, how can we solve this? So this is sort of how embeddings can help now. This is a 2-towered network. We have been calling it split net, wherein one side of the network is embedding your users, and the other side is embedding the tweets or any content for that matter. At the top layer, you're forcing a dot product with them, and you're training based on whatever business metrics you're trying to optimize for. As you can see here, this is really powerful. For either user or content-side features, you can put in pretty much anything. You can do multimodal features. You can use image. You can use text, whatever, or other features that you've curated over time. You can use sparse features or dense features. And what that gives you is now you have them in the same space. A user being close to a tweet has a meaning there. And it scales. I'll go into how it scales. After you've done your training pass, you use your content-side network to do a forward pass on all the content IDs, and you index them in a nearest neighbor index. Once you have that, what you're really doing at runtime is you're doing a forward pass given a user on the user side of the network. You get the user embedding. You query that on your nearest neighbor index, which contain all your content, or tweets in this case. Now, why the scales is the magic here is because this nearest neighbor index is not 100% precise nearest neighbor. It's approximate. There's a whole literature of work on approximate nearest neighbor indexes. This is, again, an area where we have invested a lot in the past, and we have something that we are working on our own. And what this promises is this scales in terms of log. So it scales logarithmically. And what you get is that by compromising some recall, you're actually getting a large gain in terms of your latencies. And that's really powerful. That's all you need here. And the state of the nearest neighbor indexes, it has kind of come to a stage wherein right now we're able to get 99.9% recall in 1/10 the time that it would take for me to exhaustively search everything. And it can go from 1/10 to 100 based on sort of what your real use case is. So this is really powerful, and this combination now, as you can see, actually gives us the power to use machine learning on top of, while still scaling the system. And as you can all see, compared to heuristics, this gives us the power that we are now able to optimize for any given business metric. And we can start working at that with that level of confidence, even at the candidate generation level. Usually this happens at the rankers. So nearest neighbor search, as I said, it's an essential component for candidate generation pipelines when coupled with embeddings. And it also finds applications in many other areas. Query expansion, similar XLOOKUP, meaning you given a tweet, give me similar tweets, given a user, give me similar users, et cetera. Last of all, transfer learning. This is where kind of another way where embeddings really shine, where you're training for one task, and you keep in mind that task is sort of general enough that it has applications across your other product surface areas. You can then actually exploit that in many different ways. If it's a module in itself, you can actually fine-tune that in a different, let's say, word-to-vec. You learn your word-to-vec on the tweet corpus, then you can fine-tune it according to various different text models that we have in the company. In certain ways, it's attractive from a business point of view because this work is done in one single team, and everyone else is able to kind of benefit from it and get better models as a result. Cross-domain information sharing is also very important, wherein I'm able to create this model or create these embeddings from, let's say, the most archetype product surface area that we have, and then I'm able to use that across different product surface area. I don't have to redo that work. A quick example would be, we have learned user embeddings based on follow graphs. Now we can use that in the candidate generation use case. We can use that for doing user-to-user lookup, and there are like multiple umpteenth examples that can come up with. Last of all, like what enabled all of this for us is sort of what we call the Embeddings pipeline that we created. I'll go into the details of that, but before that, quickly wanted to kind of share the goals behind the concept itself. First of all, quality and relevance. If you are doing, the first and foremost sort of the promise is that you'll get better quality and relevance. So you have to keep some things in mind beyond that as well, which is you should be able to enable, you should be adapting to evolving data distributions over time. I have a quick example to show why this matters in a minute. If applicable, the learned embedding should be of value across ML models. Then if you're doing this, then creation and consumption should come with these. No one should have to really spend months in actually consuming what you've created. So we would like, at the time, we would like to enable teams to learn embeddings at scale using the appropriate algorithm. So we have like a motley of algorithms. Given the use case, we can just pick the best one for that. Also, we would like to enable teams to consume embeddings at scale, by which I mean, if you are actually doing an online lookup, you should be able to serve their latency SLAs. It should, without really much work, you should be able to look it up from a key value store, look it up in batch settings with ease. You shouldn't have to do work for that. Sharing and discoverability is sort of the cherry on the top that actually allows people to see what's available, quickly access that, then in easy ways. Cool. This is what largely sort of the steps look like in our embeddings pipeline. The first two are sort of in the same way in item selection and data preprocessing. Then goes the stage of model fitting, wherein we have a bunch of algorithms where you can choose from. Benchmarking is sort of the critical phase here, and this loop here is no trivial one. This takes the longest time. You keep doing that for a while. At the end, you actually push what you like to the feature store. We have a feature store conception. We've been talking about this in the conference with various different companies. We have our own as well. And what that does for us is that once we have trained an embedding, as long as we have a good integration point with the feature store, it just rolls from there. People can consume, teams can consume it online, offline, version it. There's a lot of complications that we get into embeddings with versioning in feature store, which is not really a thing with normal features because there is a model involved. So we have to take care of those kind of complexities. But as long as you have this integration in place, your consumption becomes really easy, and that's a must. Lastly, all of this is sort of automated within the abstraction of ML workflows, and that is sort of a must. I'll give you a quick example to show that. These are our word-to-vec embeddings. And on x-axis, you see the time component every 6 months. Dot product similarity on the y-axis. So between President and Trump, you can see between May 2014 to November 2017, the similarity has kind of gone up. And similarly for President and Obama, it has gone down. You can see for other things as well, Twitter, Cortex, Google, and Pitchay. As these events happen, you can capture these in your embedding spaces. So this is powerful. So this is exactly why you need them to train on a cadence. You can't miss this signal, or your downstream models will be doing something funky. Getting back to sort of the stages of the pipeline, the first one, item selection and data preprocessing. This basically comes down to identifying the set of entities to learn embeddings for. Do you want to learn it for a user? Do you want to learn it for a word? Whatnot. Once you have that, you need to kind of frame your problem, frame your machine learning problem as to how you want to learn that embedding, represent those relationships in your data sets that you want to exploit. Once you have that, the data representation is actually a factor of your learning algorithm in the next stage. So you need to take that into account. I'll go into the details of the algorithm, but it will make itself obvious why you need to consider that in this stage itself. So once you have that, once you have the data and the features that you need in a particular format, you can basically get going with the different algorithms that we have in the model fitting stage. We have a bunch of pre-built algorithms, and the way we have built them is through exercising them on various different use cases, and then we kind of standardize and make them reusable. So SVD, ALS, standard ones for matrix factorization, skipgram for modeling co-occurrence, two-tower networks that I talked about for co-embedding, and that can be used for candidate generation use cases. Graph convolution network is sort of the new thing that we are investing in and trying to work out, because a lot of the data sets can be constructed in graph form when you're at Twitter. And so what can these give us? This is something we are exploring early stages in. Another essential component is benchmarking. At the same time, it's sort of one of the most difficult and challenging. You can have some standard benchmarks. Let's say for user embedding, can I predict, given the embedding, can I predict the topics that the user has shown interest in on the product? So these are more like sanity checks. After you do the first run, they don't really give you enough resolution that you might need. Qualitative assessment, this is really important during debugging and development phase. Once you have your embeddings, can I do quickly TS&E on the large scale and have tools to visualize that without really any effort? Can I really search for one of those and look at the neighborhood? These are very critical at development phase. Again, we have another tool wherein we can actually choose the type of entities, tweet or user, and the other type of entity, give the ID of the query, whether a user ID or a tweet ID, and we'll get the nearest neighbors of that. So these are the results. You can quickly inspect them, have your colleagues inspect them, figure out any anomalies, any insights that you might have, and then go and do on the next iteration of your model. Feature store, lastly, as I discussed, provides a lot of value, not only in terms of consumption, but actually this is what enables discovery without any effort on our side. Once we have things registered, you can search for them, you can look them up through a UX. It's very easy and neat from there. What's next? As I said, we are investing in more learning algorithms that can kind of allow us to harness the power of embeddings, and there are a bunch out there. We are doing that. Increasing number of data sets available. We have only gotten started. We have a few kind of mission-critical ones. We'll continue exploring in that area. Large-scale approximate nearest neighbor is sort of a whole thing in itself. There's a lot of Twitter-specific requirements that we want to kind of meet there, real-time, large-scale, having filtering criteria over there, all of that. Incorporating populated bias, diversity of results. These are like usual recommendation system challenges. With that, thanks for having me. It was real fun there. Last day a little bit.
Thank you, Abhishek, for giving us insights on ML workflow, Cortex, embeddings, and candidate generation at Twitter. Would you like to take some?
Yeah, that's fine.
If anyone has questions, we have time to take a few of the questions.
Yes, please. So, so the question is, what is the storage layer for your embeddings? So from our perspective, it's sort of encapsulated by the feature store itself. Feature store itself is actually using an in-house solution. We call it Strato, and that's what we use for that. Yeah. But it shouldn't be any different from anything else. You basically have 100 numbers. You can use pretty much whatever satisfy your thing. For the key value store, you just need, again, you can store it as whatever. Or the only thing you need to keep in mind is sort of your query latencies. It doesn't have to be anything special as far as the storage itself goes. Yes, please.
Oh, it's very loud. Do you have like an automated process for extracting from a neural network, like splitting it into the part that goes from input features to the representation layer or the embedding layer, and then another part of it that goes from that embedding layer to the actual prediction?
Yeah. So you meant the two-tower network that I was talking about?
I think so, yeah.
Yeah. So yeah, we have automated that through, again, ML workflows. Once we have our data set there, you can actually, you store one part of the network that you want to do inference on, that automatically gets to an online service deployed to that. The other part, you do a batch inference on that, automatically index an ANN service, becomes available for your UX for debugging purposes, for online serving. But that's a good question because that's sort of the meat here. It was a very long and difficult process when we started with it. And if we have to iterate fast and get to good results, it had to be all automated. So that was a bunch of effort to get there. Yep. Yes, please.
So you mentioned dot products between the embeddings for tweets and users. My understanding would be that they are both different feature spaces. So how are you able to run a dot product on sort of two different vectors with two completely different feature spaces?
Yeah, so that's exactly what your two-tower network is forcing in the network itself. You're coming from different spaces, but because there's this product thesis that a user should be there are similar users who should be close to similar tweets in some space. We don't know the space. Yeah. And that's what this architecture is forcing that to happen, right? And you're forcing that within the architecture. It's not there from the beginning.
Okay.
And that's what the power is. You can feed in whatever, and you'll get it in the same space.
All right, nice.
Yeah. Yes, please. Yeah, yes. Yeah. That's exactly the challenge that I was talking about with versioning. So we had to tackle versioning. We have major versions, minor versions. So the way you can think about that is once you train a new model for an embedding, that's a major version. But I can do inference every day on the same model. That's a minor version with the same major version, right? So when a downstream model is consuming it, it needs to be cognizant of these versions. It can't just keep consuming anything else. It can keep consuming a different minor version, but the moment it goes to a different major version, it has to retrain itself. Does it make? So so our feature store supports, let's say, we can have last 2 snapshots of major versions, but that gets really, there's a bottleneck on the storage because we have trillions of, the space is huge. It goes into hundreds of TBs for every major minor version combination. So we can't just keep everything. We give some flexibility to customers to maybe use last 2 or something like that. Yeah.
We have one last question.
Yes, please.
So in that ratio of input to the outputs in the embedding layer, how sensitive and how do you search the size of that output layer? You say hundreds, but do you go in increments, 100, 200, 300?
Yeah, so that's more like a hyperparameter. You just have to kind of find your best fit there. And to be kind of frank, maybe you'll not even see the differences in the benchmarks or the way we have to measure, maybe going from 300 to 350 or 400. But what you really see is maybe 400 to 1,000 makes a difference, or 400 to 100 makes a difference. Yeah, thanks.
Let's hear it for Abhishek.
Thank you.